All right, we got about 40 seconds before we start the class, and today's lab is already released. But before we move on to floating point numbers, I think I'm gonna go back and kind of go over the flags a little bit. The overflow flag, how it relates to the sign flag, and how to compute the overflow flag. So that's something that we'll do in 10 seconds. And I'm going to try something here. I'm going to try to turn on my camera while at the same time turn on the screen, and it actually works. That's interesting. Okay. But can I still look at the text messages at the same time? Yep, I can do that. Excellent. Okay, great. I turn on the camera because sometimes I have gestures, like quotes and stuff like that, that you cannot see just from hearing my voice. I can also put a picture in picture, that doesn't. So I think if you look at my screen, and if you look at my video, you cannot look at the screen at the same time. Is that correct? Or can you guys look at both at the same time? Hmm. Cannot do both at the same time. So yeah, I guess the video would not be very helpful in that case. I can do a picture in picture because a picture in picture means it will also be captured in YouTube. So that would be helpful for people who just watch the YouTube. So I'm going to do that, unless somebody has an objection to that. And let's see. Okay, a few people typing. Alright, so here we have settings, stream, note, has not do. And there we go. So I'm gonna add another source over here. Okay. And of course it has to put me at a place that is obscuring the most of the screen. So let me change the resolution, because you only have to see my gestures, like when I put quotes and other gestures, and then I can move it to hopefully a inconspicuous place on the screen that does not affect or interfere with explaining items in the class. Okay, cool. All right, so now we're gonna get started with the class. And there were quite a few questions, on today's text channel already. So I'm gonna address some, if not all, of those questions. One of the questions, or a few of the questions, has to do with how overflow is computed. So what I want to do is to kind of go back to the lecture from yesterday. And of course, me being me, I have once again misplaced my tablet pen, which means it cannot be charged unless I put it back into its garage for a while, which is okay because I can always explain it using mousepad for now. There we go. Alright, so Martin is asking, can I do an example of the overflow formula of the two problems? One is 0011 minus 0111, and the other one is 0111 minus 0011. Okay, so let's go ahead and do that. And I'm using a mousepad for this purpose, just because the tablet stylus needs to be charged in its garage. So what we'll do is do this in 0011, and this is in base 2. So as a signed representation, because when we talk about overflow, we are always talking about signed interpretation of a bit pattern. So in this case, 0011 is representing the value of 3, and then we want to subtract 0, 1, 1, 1 from that, and 0, 1, 1, 1 is representing the value of 7. And now we have this row which we know as Q, and this row here starts with a 0 because that's the least significant digit, and we don't have any digit to the right of this column, and this is what we know as T in the subtraction. And then lastly we have the D row, which is the answer, that's the difference row. Alright, so let's go back here and try to figure out what we have here. 0 minus 1, 1 minus 1 is a 0, and then 0 minus 0 is a 0. And neither contributes a borrow of 1, so the borrow of the next digit is going to be a 0. 1 minus 1 is a 0. 0 minus 0 is once again a 0. And neither subtraction has a borrow of 1. So on the next column, the borrow is also going to be a 0. This time we got something slightly more interesting, because 0 minus 1 is a 1 with a borrow of 1. And then 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with an overall borrow. So that's how we compute all the bits. So with all these bits, we kind of have to look at this and go like, all right, so what are all the flags that we have talked about in this particular case? So we want to look at the overall borrow flag, and the overall borrow flag is this bit over here. Okay, it is basically, in this case, it is also known as T4, because it is on column 4, because we come from 0. So that is a 1. When we look at the sign flag of the difference, it is D3 in this case, because it is on because it's digit 3 of the difference. That is a 1 as well. When we look at X3, that is a 0. When we look at Y3, that is a 0 as well. Are we doing okay so far with this? Because X0 is this bit, Y3 is this bit over here, and then D3 is this bit over here. So are we still doing okay? All right, okay. So assuming we're doing okay, and if we are not, if you need a little bit more time to digest, just let me know. You can just type something on the text channel, and I'll go ahead and give people a little bit of time to absorb the material. So now we want to compute the sign flag. The sign flag, which we also know as S, is basically the same thing as D3 in this case. Is the most significant bit of the difference, and that one is a 1. So the overflow flag is the more complex one. The overflow flag is a 1 if the sign of the result, or in this case the difference, doesn't make any sense. So the question now is, if I subtract a non-negative quantity from a non-negative quantity, can I end up with a negative quantity? And the answer is yes. So from that perspective, which is the semantics of overflow, it should be a 0. Okay, but I don't like to look at things from the semantic perspective, because after all, this is low level. It's computer science, but it is at a very low, transistor / gate level. So we want to look at it from the perspective of logic gates. And in this case, overflow, okay, if you remember from the lab from yesterday, overflow is expressed like this. And this time I'm going to use a whole bunch of extra parentheses. So it is D3 in this case, okay, negated X3, oops, excuse me, I have to put it in the right order. So it's X3 first, negated Y3, and then we have another negated D3. So this is one way to make the overflow a 1, but there's another way. The other way is negating X3 first, and then have the other two non-negated, like so. Okay, so yes, I know some of these parentheses are not needed, but I just want to put it all in so this is extra clear, what we are negating and what we are ANDing, as well as what we are ORing. So in this case, if we just plug in, x3 being 0 over here, y3 being 0 over here, and then d3 being 1 here, then we know that we are having 0 and 1 and 0 over here, which will give us an end result of 0. So I'm going to use this to represent, after we end everything here, that becomes a 0. So let's look at the right hand side of this calculation. x3 itself is a 0, y3 itself is a 0, d3 itself is a 1. Then we look at the negation, but this time we're only negating the first one, which is the x. So that becomes a 1. So now we have 1, 0, 1 over here, and then we make the conjunction out of these three. So once again, I'm going to use this to represent, we are ANDing, 1, 0, 1, and that is also a 0. So when we have 0 or 0, then the end result is just 0. So we have all of this ORed with this, and that just gives us, a final answer of 0. So overflow is 0 in this case. So are we good so far with this? All right. So let's go ahead and work on the flip side of this. So the flip side of this, okay, I'm going to reuse the same format, just because I don't want to have to redo. Well, I suppose I can just copy and paste. All right, so that's what I'll do is copy and paste. So I'm copying all of this and paste it here. And obviously we have to change a few digits, to make it work. All right, so let's work out all the Q and the other bits again. Okay, that's a 0 over here, and all of these we do not know yet. Okay, so there we go. So we have 1 minus 1, which is a 0, and then 0 minus 0 is a 0 with no borrow of 1 from either one, so this is going to be a 0 here. And then once again we have 1 minus 1, which is a 0. 0 minus 0 is a 0, and neither contributes a borrow of 1, so the next borrow is going to be a 0 again. 1 minus 0 is a 1, 1 minus 0 is a 1, and neither contributes a borrow of 1, so we have a 0 over here. And then we have 0 minus 0 is 0, 0 minus 0 is 0, and we have no overall borrow of 1 in this case. So that is that's basically all the bits that are coming out of the subtractor. So we go to here, and then we say the overall borrow is going to be a 0 because this T4 is the overall borrow of the entire subtraction. D3 is the most significant bit of the difference, which is this one over here, and that is a 0. X3 and Y3 are both zeros, okay? So in this case, the sign is going to be a 0. So when we move down here, we look at all the bits, and all 3 bits are zeros. So when we negate, we end up with this situation. So even though in the conjunction, now we have 1 more 1 in this particular conjunction, but the overall result is still false because we still have x3 being false by itself. So not y3 being a 1 and not d3 being a 1 does not help, and we still end up with the result of the conjunction being a 0. On the other side, the change is d3 is now a 0, and we're only negating x3 in this case. So this time we have 1 and 0 and 0, which is a 0. So once again we have 0 or 0, which means the overall overflow is also a 0. There is no overflow in this case. So that's Martin's question. And I'm hoping this also helps with people who might have a little bit of a struggle, trying to understand the concepts. All right, so I'm waiting for Murtaza to type his question. Not seeing anything. All right. So have I addressed all the questions, from today's text channel? All right. Oh, okay. So Martin is typing. All right. So from the lecture, 0, 1, 1 or 1, 0, 0 would be a 1. Okay. So that is referring to. Okay. So let me quote the text over here. All right. So the okay. I am going to simplify the terms a little bit. So M, okay, let me explain what each one is. M is the most significant bit of the minuend. S is the most, the most significant bit of the subtrahend. And then we got D being the most significant bit of the difference. Okay, so this way I don't have to type, all the suffixes and whatnot. So given this is, how I am using the terms, overflow is defined to be M not S not D, which means M and not S and not D, or not M and S and D. So that means we have two chances to make the overflow a 1. The two situations to make overflow a 1, overflow is a 1 if and only if, okay, there are two scenarios. M is a 1, S is a 0, and D is a 0. Or M is a 0, S is a 1, and then D is a 1. Those are the two scenarios that can make overflow a 1. And that is why I talked about 1, 0, 0. The 1, 0, 0 is referring to this particular scenario, where the most significant bit of the minuend is a 1, the most significant bit of the subtrahend is a 0, and then the most significant bit of the difference is also a 0. And then the 0, 1, 1 is the other side, is the flip side of this, which is, you guys get the idea, I hope. So is that kind of explaining, does that explain the picture from the previous lecture? Because this really is the same thing as the picture that you posted. Because the picture that you posted has to do with a truth table. So the 0, 1, 1 is referring to the row where xm minus 1 is a 0, ym minus 1 is a 1, and dm minus 1 is a 1. And I think my tablet is reasonably charged, so let's go ahead and take a look at that. Okay. All right, so what Martin is referring to are these two rows. But you can see in the green, the one that is circled green, xm minus 1 is a 0, ym minus 1 is a 1, and then dm minus 1 is also a 1. That is what the 0, 1, 1 is coming from. That condition, when x is 0, y is 1, and then d is 1 again, I'm only talking about the most significant bit here. That is the time when the conjunction over here will give you a 1. And then likewise, the orange one is referring to another row where overflow is a 1. And in order to use that particular conjunction, to make that conjunction a 1, then we need x to be a 1, y to be a 0, and then d also to be a 0. So I hope this clarifies what that truth table is talking about. Can I show the scenario to trigger the overflow? Yes. In fact, we have done it already. Okay, so what we'll do is we're gonna take a look at the examples that we have done so far, and we'll pick one where the overflow is a 1. Okay, so this one will work. Okay, so I'm gonna kind of write over what we had last time. So when you look at this scenario, okay, look at these two bits and look at this bit over here. This is xm minus 1, this is ym minus 1, and this is dm minus 1. Okay, so that is going to make overflow being a 1. So in this case, overflow is a 1 because we have xm minus 1 being a 0, ym minus 1 being a 1, and then dm minus 1 being a 1 as well. Now we have another example to illustrate how to make it overflow. It's this one over here. So with this one, we have 1, 0, and 0 over here. So this time we have xm minus 1 being a 1, ym minus 1 being a 0, and then dm minus 1 being a 0, and that also causes the overflow to be a 1. You're welcome. Yep. So these two particular examples from yesterday was used to illustrate why we cannot only rely on the sign flag. Because if you ask a mathematician, the mathematician would just say, well, the sign flag should be sufficient. Because if x minus y is less than 0, then we know that x is less than y. Well, that is true in general in math. But when x and y and the difference only has a specific range, and we are talking about modulo arithmetics, then it doesn't work because there's a possibility of overflowing, and when it overflows, then the sign bit doesn't really tell us the proper result anymore. And these two examples, okay, being this one and also this one over here, illustrates when we have an overflow situation and we cannot in those cases trust the sign flag. In other words, the sign flag is wrong. Okay, when I say we cannot trust the sign flag, it's basically saying the sign flag is wrong. But since the overflow flag says the sign flag is wrong, we just have to flip the sign flag to become the quote unquote proper one. And the exclusive or between the sign flag of the difference and the overflow flag, which I call the L flag, is going to accomplish that. So do we have any additional questions about the flags, how we compare bit patterns? Okay, so it looks like we do not have any questions or further questions about the flags. So what we'll do now is we're going to move on. Okay, this is a fast-paced class because it's a 16-week full semester class, 4 units compressed into 8 weeks. So we're its time is kind of compressed in this case. All right, so there are a few things I need to talk about. The first one is we have an exam on next Wednesday. Okay, so I sent an announcement to everybody already, and I also sent a form to people, and so far I got 19 responses back. And obviously, there's no single time slot that everybody can make it to. Let me just kind of check on the time slots over here. I'm not going to name names, but I just want to indicate what I get, just so that you guys know what I'm dealing with. All right, so with the 19 responses that I got so far, um, some people basically block off pretty much the entire day except for, okay, I'm just going to look for the most extreme cases here. Some people only block off like 3 of the time slots, which is not a big deal. One person blocked off 6 of the time slots, leaving only 3 open, but that wasn't the worst. Well, in terms of having time slots blocked off. Um, nope, that was actually the one that blocked off the most. But the bottom line is I cannot find a single time slot where everybody can make it to, which is well, it's going to be a challenge for me because this is an online class. I cannot require everybody to make it to a single time slot. Um, but the challenge to me is in the previous semester when COVID-19 hit and we had to go online, everything is done online. There is a surge in terms of academic dishonesty, otherwise known as cheating. I caught, let's see, 4 or 5 cases, and in some cases there are 2 people involved, one person contributing the answer or helping the other person, and then the other person receiving help during the test. And I have never seen this kind of frequency before when I had face-to-face exams. So my challenge is to make sure that there's no such thing happening in the exam. So when the test it cannot be scheduled within the same time slot, there's a little bit more. Um, it presents more of a challenge to me to make sure that no cheating happens. So that's kind of what something that I have to deal with, and I'm pretty sure I'll figure out a way to do it. So this is a good time also to kind of bring everyone back to the syllabus. So I just want to go back to the syllabus and revisit a particular point just so that people cannot say that I did not mention it. So the point I do want to mention has to do with academic dishonesty and particularly the consequence part. Okay, so if you have not read the syllabus, you probably need to read the entire thing. Okay, I'm not implying anyone in this class is planning to cheat, but I think the entire syllabus is actually useful. So in this case, every single case is going to be reported. In other words, I don't really, there's no differentiation whether this is the first case or the second case. Every single case is going to be reported to the student conduct person who is actually an associate vice president of the college. So, I just want to make sure that this is known to everybody before the first exam. Okay, in the previous semester, I have had people begging me not to report it. Okay, they admitted to it and begged me not to report it. They even tried to convince another professor to convince me not to report it. And guess what happened? I reported it because if I said I would do it in the syllabus, I am going to do it according to the syllabus. I cannot say one thing in the syllabus and do something else. Okay, that is not something that I can do. All right, so that's just kind of something I want to remind everybody about. I'm not assuming anyone is going to cheat, but it is something that is on my radar, and it is something that I personally need to handle. Yeah, so the one person mentioned, through direct message, mentioned that I should put this schedule on the Los Rios class schedule. Um, the problem is, because it's an online class, it does not have a particular time associated with it. I don't think, that it would let me, specify a specific time. And also because we cannot go on campus, in some situations, people, professors have specified that exams are face to face, and people have to actually go back to the classroom to take a test. But I can't do that either because of COVID-19. So I will figure out something. Okay. it is not. Oh, math classes do that, huh? Okay, I will check that out. All right, but I have my own ways of handling uh, you know challenges like that. So that being said, so what we'll do is we are moving on, and we are going to continue to talk about floating point numbers. So the scope of the test, okay, I'm pretty sure some people have that in their mind already at this point, which is what is included in the exam. I am going to include everything up to and including um, number comparison, binary number comparison. So what I'm going to introduce now, which is floating point numbers, is not going to be in exam 1. Now the reason why I'm not going to include it in exam 1 is simply because there may not be enough time for people to ask questions about floating point number topics, and it has several labs. Today we're only doing the first of the several labs related to floating point numbers. So I want to make sure that we have a chance to go through all of the labs before I put floating point number as a topic in an exam. So it's got to be in exam 2 and not in exam 1. All right. Okay. All right, so the questions are not like the labs. The questions are going to be more open-ended. So I'll be asking people not only to give me the answer, but also to explain the answers. So any correct answer without explanation is going to get a big fat 0. So because I want to see how people reason, and not just that they get the final answer, because some of the questions you may actually be able to use a calculator. Go online, get a calculator, and actually get the result. So that's not the focus. The focus is how do we get to the answer. All right, so okay, so let's go ahead. Oh, okay, Robert is typing. Let me wait until Robert is done typing. How many questions are usually on the exam? Well, this is a little bit different because I have to change the format of all my exams because of everything being online. So I do not yet know how many questions there will be in the exam. Typically, before COVID-19, for the first exam of this class, I'll give you guys a practice test, maybe sometime next week, like maybe Monday. But typically, I have maybe 5 or 6 questions, in before COVID-19, before this class went online. Now that the class is online, okay, and I do let people use the internet while taking the test. So people can Google, people can go to Wikipedia, people can even look up binary calculators, okay, those are all fine, okay. So I'm making the assumption that people would do that. And that's also the reason why I have to change the type of questions, because before COVID-19, when everything was face to face, calculators, other than the simple calculator, were only simple calculators were allowed in the exam, and no other electronics are allowed. But now I'm opening up the entire internet, which means certain questions are pointless. And I will have to kind of think about what kind of question I can ask to really assess whether people understand the concepts and be able to problem solve at the same time. So I do not yet know, to answer Robert's question, I do not yet know how many questions will be in the exam. And then Murtaza is typing. I'm gonna wait until I see the question. It becomes harder. You mean the exam itself, or it's harder for me to come up with the questions? Or both? Yes. Well, it is both. Okay, Catherine is correct. It is both. Um, I look at it as a challenge, and so I will have to think of ways to make the exam challenging enough and not too hard, and also at the same time, I'll be able to curb cheating. So it is a challenge. It's going to be an interesting challenge this time, especially because I cannot schedule everyone to take the exam at exactly the same time. All right, so now we are going to move on to floating point numbers. Unless anyone has any additional questions, I'm going to move on to floating point numbers. I got 2 people typing in Discord, so I'm waiting a little bit. It's probably not likely that I can schedule everyone to have the same block, because there are 19 people who responded, and the more people in the class, the less likely we can find a common time slot. I can kind of block people into like 2 major time slots, or maybe 3. I think I have to use 3 because there are 2 people where their available time slots were mutually exclusive. So we need at least 2, but I think we need 3 specific time slots. So I'm going to take a look at the availability responses again, and then I'll just go ahead and schedule 3 individual time slots for people to take the test. So for each one, everybody's going to start at the same time and end at the same time, but there will be 3 different sessions basically. Oh, don't worry, Martasa, your English is fine, so no worries. It's just that you have to be more specific when you mention something. That's all. All right, so let's move on to floating point numbers. And floating point numbers is something that you know already, or at least I think most of you know it already. We know it as the scientific notation in base 10. So what I'll do is I'm going to take a look at that and give some examples just so that people understand what I mean when I say the scientific notation. So starting a new page. All right, so scientific notation looks like this. Okay, this is just an example. So if we look at, let me look this up, okay, just so that it is not a random example. I'm just going off screen a little bit here to look up a number that is kind of interesting. Okay, there we go. So when we look at the speed of light, okay, the speed of light is, okay, I'm just quoting this from a Google search. Okay, so 299,792 km per second. Okay, that is the speed of light. So when we look at the speed of light, and you go like, well, I don't really need to know, 299,792. If we just call it, 300,000 kilometers per second, that's good enough. Okay, so we go like, okay, this is approximately 300,000 kilometers per second. Okay, that is not in scientific notation. This is not scientific notation. So what scientific notation is to convert this into a format that looks more like this. It is 3e, and let me just count here, 368, okay, 3e8 meters per second. Okay, so I'm not using the kilo because kilo is just 1,000. So I'm folding all of those units into the numerical part, and then the unit part would just use the SI units, as themselves. Okay, so we are not using kilometer, we're just using meter here. Okay, so this here is scientific notation. So scientific notation has 2 major components. One component is I'm going to look this up too, because I keep calling this the mantissa, but apparently it is not the actual mantissa. So I'm looking up mantissa off screen. You cannot see it. It's the part of a number located after a decimal point. So that is not the actual mantissa. But I do want to find the proper term. Double precision. It is possible that it does not actually have a particular name, so in that case I can't really refer to it using a particular name. Okay, I'm looking at one page, all it says is, this part here is called the digits. And, and then the E means, times 10 to the power of, and this 8 is that. Okay, so when we read this entire thing, it means it is 3 times 10 to the power of 8. So are we okay so far with understanding what a scientific notation is? Okay. All right. So let's use another example. Okay. So using scientific notation, it is very compact, right? Because in this case, I would have used a lot more digits, to express, 3 times 10 to the power of 8. And the scientific notation is really easy to specify, the same quantity. So now let's take a look at the size of a transistor in the latest AMD processors. Okay, so I already know what that number is, but I'm going to give you guys a chance to tell me what is the transistor size inside the latest AMD processor. Does anyone want to contribute? You can Google search right now and then type it in the text channel if you want to. All right, 7 nanometers. That is correct. Okay, so what is 7 nanometers? Okay, so a nano, if you look it up, is 10 to the power of -9. Okay, so 7 nanometers, 7 nm, is actually 7 times 10 to the power of -9 meters. So the scientific notation is now 7e minus -9. Of course, the meter is the unit, but it's outside of the quantity that we want to specify. So is that okay? Does everybody understand what a scientific notation is? Okay. I'm guessing it is okay at this point, that there are no questions about what is base 10 scientific notation. Okay, all right, excellent. So a floating point number is basically a scientific notation in base 2. That's it. Same concept, okay? Same concept where you have a quantity that you specify in quote unquote the digits, and then you have an exponent. But this time the exponent is not an exponent of 10. And can anyone guess what is the base that we're going to use for this exponent when we talk about floating point numbers? It's in base 2. Very good. Okay, so Catherine is correct. It is in base 2. So let's go ahead and take a look at an example. Okay, so I'm just going to pick a random example in this case. We'll say 1.011 in base 2 times 2 to the power of 3. Okay, this is a base 2 scientific notation where we have the digits and then we have the exponent over here. So what quantity is this really expressing? There are several ways to do this. There are several ways to convert a scientific notation in base 2 into the value, to understand the value of a base 2 scientific notation. There are several ways to do it. So I'm going to do it, the first way, which is kind of, a little bit awkward, but I think it'll be okay. This one tells us that we have 1 times 2 to the power of 0. This 0 tells us that we have 0 times 2 to the power of negative 1. This 1 is telling us that we have 1 times 2 to the power of negative 2. And this 1 over here is telling us that we have 1 times 2 to the power of negative 3. So this is going all the way back to base conversion, and also when I explain what a base is and how to interpret a number. So when we add up these numbers, okay, this is just 1 because 2 to the power of 0 is just 1, and this one is 0. This is 1/4, and this is 1/8 over here. So when you add up all of these, we have 1. If I want to use a mixed fraction, then we have 3/8 over here. And if I want to just use a fraction, it is 11/8. What about this part over here? It is 2 times 2 to the power of 3, which is 8. So now we got 11/8 times 8, which is really just 11. Now this is base 10. In other words, 1.011 base 2 times 2 to the power of 3 is just what we know as 11 in base 10. Are we okay so far? Does everybody understand what I just did to figure out the actual value of a number that is in base 2 scientific notation? All right, excellent. So now that we understand the basic idea, okay, I'll just kind of talk about why this is a really useful representation. It's a really useful representation because given a certain number of bits and splitting some bits to specify the exponent and some bits to specify the digits, I can specify numbers or values within a really big range. Okay, now that all depends on how many bits I allocate to specify the exponent. Okay, so when you look up what is a double precision floating point number on the internet, the first page you would probably find is Wikipedia. So let's go back to the notes over here and look up the scientific notation. And this link here will bring you to the Wikipedia page, which has a kind of nice pictorial representation of how the bits are allocated. Okay, you can see how they use color coding and make it very easy to identify which part is which part. So they also even explain, okay, not surprisingly, okay, they did a pretty good job explaining what is the value of a 64 bits packed in this particular way. Okay, what you see here from 0 all the way to 63, those are the digit numbers. So we have bit 0 of the entire 64-bit and up to bit 63, which is the most significant bit of the 64 bits. But when we look at the value, when we want to figure out the value of a double precision floating point number that is formatted this way, we're not just going to add up, oh, okay, we have this digit times 2 to the power of 0 plus this digit times 2 to the power of 1 plus all the way up to this digit times 2 to the power of 63. We're not going to do that because different parts of these 64 bits serve a different role when we try to figure out the value represented by a double precision floating point number. This portion here, the portion that is kind of in a salmon color, is actually the fractional part after the 1 point of the quote-unquote digits that in the notes I call it the mantissa. And then this portion here, which is all in green, that is the portion that specifies a biased exponent. I'll explain what I mean by biased. And this part over here, the light green part, is specifying the sign. If it is a 0, it means the value is non-negative. If it is a 1, it means the value is negative. So you can choose one of these two ways to kind of interpret the value, to find the value represented in the double precision floating point number. Now, one is a little bit more intimidating. Catherine is asking, what about the digits to the left of the decimal point? It is implicitly a 1. In other words, there's always a 1 point and then followed by the salmon color digits. Okay, I'll give you guys an example later on. All right. Okay. So when you look at this equation here, or this equation over here, formula, I should say. So when you look at this formula, we kind of know the actual exponent of 2 is whatever the unsigned number that the green part of the um, double precision floating point number is, minus the constant of 1023 in base 10. That becomes the power that we raise 2 to. Okay. And then what about from bit 0, which is all the way here, to bit 51, which is all the way over here? That becomes the fractional part of the quote-unquote digits of the scientific notation. So this 1 point here is non-negotiable. It is always here. And that is also why when you look at the sigma notation, we have a 1 plus that is outside of the sigma. It is always going to be 1 point something. It's always going to be at least 1 if you look at just this portion of a double precision floating point number. And then some of you are going to be asking, but then how do we represent 0, right? Yeah, we'll deal with that later. That is a minor issue. We'll deal with how we represent 0 a little bit later. So what about the sign of the entire number, the sign of the value? Now, this sign does not apply to the exponent. It applies to the entire value. It is -1 to the power of sign, which is a single bit over here. So the sign bit can be a 0. If the sign bit is a 0, -1 to the power of 0 is going to give you a value of 1. And that's why the value becomes non-negative. On the other hand, if the sign bit is a 1, then -1 to the power of 1 is -1, then the value becomes negative. So that's a really kind of quick way to look at this. So now what we want to do is to look at an example. Okay, so we'll go ahead and look at an example, and we can do all of this by hand first. So we want to look at a 64-bit number, okay, and I'm not going to spell out all 64 bits because that's going to take a while. So I'm only going to specify a few of those bits. So we'll start with a 0, and then we'll have 1 0 0 0 0 0 0. I have to kind of keep count of all this stuff here. 0 0 1 1. Nope, 1 0. That's what I want. And then we want to specify 0 1 1 0, and then the rest are all zeros. Okay, so we want to look at this bit pattern here, and I'm going to specify the exact bit position using a different color. So I'm going to use dark green to indicate the bit position. This is bit position 0. This is bit position 63. This is bit position 62, 61, 60, and let me kind of go back to the other slide here. Okay, so 52 is this guy, 51 is this guy, and so on. Okay, so we look at all of these bits, and remember, I'm trying to figure out what is the value represented by these bits, all these 64 bits, but we want to look at these 64 bits not as a single signed or unsigned integer, but we want to look at it as a double precision floating point number. So we're going to break it up. Okay, there are 3 main parts to this. The first part, okay, is this guy over here. This is our sign. Okay, and the second part would be the next 11 bits, which are these guys. This is going to be the E that you see in the Wikipedia page. So this E right here is referring to this E over here. And then this is the rest. Okay, it doesn't really have a name, but I'm just going to call this M, which is this is the proper mantissa, in a because it's the portion of a number to the right hand side of the decimal point. Okay, so we are now breaking it into 3 main parts. So the sign is easy, right? Because the sign just tells us, in this case, it is a non-negative number. All right. So the E is a little bit trickier because it is biased. If I go back to the Wikipedia page, you can see how E itself is not how we raise the power of 2 to. It is, we have to first subtract 1023 from the unsigned integer of E, then that difference becomes the actual power that we want to raise 2 to. So we're getting back to here, we want to see, okay, so what is the exponent? What is E in this case? So when we look at E, this one here is 2 to the power of 10. And then this one over here is 2 to the power of 1. So when you add up these two, we got 1026. Because 2 to the power of 10 is 1024. When we add after we add 2 to 1024, we have 1026. So the actual exponent, okay, is 2 to the power of E minus 1023. And because we know E itself is 1026, that means we just need to raise 2 to the power of 3 in this case. Are we doing okay so far? So I can call this one, I can call this the magnitude. So does everybody understand why the magnitude is 2 to the power of 3 when E itself is in binary 1 followed by a whole bunch of zeros and then 1 0? Okay. So now the trickiest part is going to be the M. What do we do with that M? So with that M, it's basically saying, okay, it's a 1 point, and then we take the entire M and then stash it over here. That is why it's the actual mantissa, because it specifies all the digits to the right hand side of the 1 point. So in this case, okay, it is 1 point, and then we just copy everything, which is 0 1 1 0 and then a whole bunch of zeros after that. In other words, we take all of this, okay, let me use a different color. We take all of this and then we just stash it all the way to the right hand side of the 1 point. Now we have to be careful because this is a base 2 number. So now we have to say, okay, what is that really expressing? That looks kind of familiar because I'm actually using the same value as before, the same example. So we have 1 plus none of the halves, 1 of the fourths, and 1 of the eighths. So it's 1 plus 1 quarter plus 1/8. And this time I'm going to call it a different name now. Okay, I'm going to call this one 1.375 in base 10. Because 1/4 is a quarter, 1/8 is 0.125. So when you add up those two, we get 0.375. But the 1 point over here is non-negotiable. So it is always going to be there. So after we look at all of these pieces, what is the value? Okay, so the value in this case is going to be non-negative. Okay, so which is 1. So this is basically the -1 to the power of sine times the value or the digits. That turns out to be just 1.375 in base 10. This is how I made the conversion from base 2, which is over here, to base 10 over here. Then we also have to multiply it by the magnitude. The magnitude is 2 to the power of 3. So if you use a calculator, or if you kind of map this back to what we had before, then the whole thing is just 11. In other words, if you look at 64 bits, which is what we saw all the way up here, and if somebody tells you, look at these 64 bits as a double precision floating point number, then the value being represented in this case is really just 11 in base 10. Are we doing okay so far with this example? Assuming that Tech knows what he's doing. So are we doing okay? Any questions about these steps? Okay, so we got confirmations. So now the question is, well, does Tech actually know what he's doing? Okay, and it's really a legitimate question. You should ask that question at least in your mind whenever you or taking a class, okay, is whether the professor knows what he or she is doing. So how do we check, right? In this case, tech make this kind of crazy claim that we are using these 64 bits in this particular format, and in the end, it is representing 11. I'm pretty sure there's some online resources that will allow you to plug in all the bits to give you the exact value of what it is representing. The reason why I said that is because in the previous semester, quite a few people gave me the same kind of result, formatted in the same way. So I'm assuming that they all got it from the same web resource to do all the interpretation. So, which means this year I'm going to have to ask questions where, that is not going to be helpful. All right. So how do we check? Okay. So how do we check that this in fact is what is happening? So what we'll do is we're going to use a very simple C program and a debugger GDB to answer this question. Okay, so Catherine is typing something. I'm going to wait for that, but I can already drag. Yes, I can share the Zerno file. Yep. All right, so what we're doing here is I'm going to write a simple program. So when I said simple, I mean really simple. What you're seeing are the devices, all the input-output devices. This is what happens when I run the script, so that I can actually use my the stylus for my tablet. Because otherwise, it doesn't know how to scale the result of the tablet to map it to the screen coordinates. Anyway, so let's go ahead and write a very simple program, and that's just quite simple. So pound include stdint.h. So by now you should know what is standard integer.h. It gives us all the types where I can specifically ask for integers of a particular bit width. And the program itself, okay, we got return 0 all the way at the end. And I'm just going to say uint64_t. So this is an unsigned 64-bit integer. We'll just call it x. And we have x equal to 0 over here, which is not actually needed for what I need to do, but I need it to be here so that the compiler does not optimize x out of existence. Otherwise, GCC, even without turning on optimization, will optimize out any unused local variables. Okay, so this is the entire program. And then somebody may point out and go like, but Tech, this entire program does not even refer to the type double. You are correct. Okay, it does not refer to the type double at all. So we're going to exit this gcc-g, which specifies that we want to retain debug information, and then -o to specify the name of the executable, and then the source file or source files if you have multiple. Okay, no problem. GCC does not complain. And now we can run it using GDB, which is the debugger. Now what I do on the command line using GCC and GDB, and also nvim, which is my editor, you can do all of the same stuff in code blocks. So if you don't want to learn how to do everything on the command line, you can use code blocks and actually achieve exactly the same result. So now I go to GDB simple and list the program, put a breakpoint on line 7, okay, and then we just run the program. So when we get to this point, we print x, and not very surprisingly, x has a value of 0. So somebody's going to ask, well, but how is that going to help us show that that entire 64-bit pattern is in fact representing 11 when we look at it from the perspective, or when we chop up the bits and interpret those bits as a double precision floating point number. So let's go ahead and do that now. Okay, so what we're looking at now is the bit pattern. So somehow I have to enter this particular bit pattern into the C program. So this is going to be the first introduction to hexadecimal or base 16 numbers, and we'll deal with it again. So don't worry if if you're not quite getting it yet. So with hexadecimal numbers, we have to group the digits into groups of 4. Now, technically speaking, we should start grouping from the right-hand side. In other words, we should group the least significant 4 bits, then the next 4 bits, and so on. That technically is what we need to do. However, because we know we have exactly 64 bits, so it is okay to group from the left-hand side. In other words, we look at these 4 and say, let's group these 4 into 1. Group these 4 into 1, group these 4 into 1, and group these 4 into 1, and so on. Okay? So now we look at each group of 4 bits, and then we convert each group into a single base 16 digit. Whoa, hold on a second here, okay? I thought base conversion involves, a whole bunch of division, taking the floor, and then we do another mod. That's how we extract a single digit using base conversion. Well, actually, it is a whole lot easier in this case because base 2 and base 16 are closely related. Can someone kind of guess why base 2 and base 16 are closely related and the conversion between those two bases is really easy? I like how you guys are jumping on, exactly. Okay, very good. And I'm gonna wait for Julian's answer too. Oh, okay. All right. So Richard is right. Okay, 16 is a power of 2. So that makes these two bases very closely related. Okay, so when we look at 16 as 2 to the power of 4, that is exactly why we can take 4 bits and then convert it into a single digit in base 16, because every 4 bits is going to specify a quantity from 0 to 15, which turns out to be also what a single digit in base 16 can do. So that's why the conversion between base 2 and base 16 does not involve division at all. It just has to do with grouping things into groups of 4 bits and then look up a table, and by the time you're done with this class you would have memorized the table already, and that's the conversion process. So now let's do the actual conversion. Okay, so I'm going to use a pukey gray color to do the conversion. So this is 0100, which is known as 4, right? I mean, that's not even a very particularly tricky base 16 digit. This is a 0. This is a 2. And this is a 6. So we don't even have to use the trickier base 16 digits, which would be from A to F. The digit A in base 16 is representing what we know as 10, the quantity of 10. The digit B is representing 11, and then all the way up to F, which is representing what we know as 15. But we don't even have to encounter those cases in this case. So if I want to specify this entire bit pattern as a hexadecimal number, it would be 0x, okay? 0x is the prefix to tell the C compiler or GDB that what follows is going to be a base 16 number. And we just have to say, okay, we got a 4, we got a 0, we got a 2, we got a 6. How many digits of zeros do I need to make up a 64-bit number? So that's the next question, right? Because so far I only got 4 digits. Out of how many? How many digits do I need? Exactly. So, why that single? Oh, you mean this 0 here? This 0 is a part of a whole bunch of zeros. So there's actually a whole bunch of zeros within this range here. Because I didn't write out exactly 64 bits. That would take a little bit too long. So yeah, so this 0 is just here to represent a whole bunch of zeros in between. Okay, so now the question is, how many more zeros do I need? And Richard is correct. We need 16 digits in base 16 to make up 64 bits. That's because one hexadecimal digit is going to make 4 bits, right? And then in 64 bits we need 16. Okay, we need 16 groups of 4 bits in 64 bits. So that means we need 16 base 16 digits, or 16 hexadecimal digits. I got 4 here, so I need to specify 12 more to make up a 64-bit number. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now I just need to enter this number into GDB. Then I have the bit pattern in. Okay. So let's go ahead and do that. So it's 4026. Okay, so back to GDB. Now we can say set x equals to 0x 4026, and then exactly what I said, 12 zeros after that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Press the enter key. Pretty cool, right? So now I want to print x, and whoa, hold on a second here. That is not anything that we are anticipating. Okay, first of all, this is not 4026, a whole bunch of zeros, which was what I entered, and this is also not 11. What is going on here? What am I seeing at this point? So now you have to think from the perspective of the debugger as well as the compiler. Okay, so if I were to ask you what is the type of local variable x, what is it? It's actually somewhere on the screen, and you can just kind of read the program and find out what is the type of x. Yep, it is a 64-bit unsigned number. Sakil is right. Okay, so the GDB, understands the type of x as well. Okay, GDB being the debugger can read the symbol table and know that, oh, I look at these 64 bits in memory, and I'm going to interpret those 64 bits as an unsigned 64-bit number, which means it's going to make a gigantic summation. Okay, every bit is corresponding to a power of 2, and it's just adding up all the powers of 2 that is corresponding to a bit of 1. And that's how we end up with this number here. Then the next question is, well, how come it doesn't even look like the hexadecimal digits or the hexadecimal number that we just put in? Because this is in base 10. Okay, GDB is trying to make things easier for humans, and so unless you ask for it, it will print everything in base 10. Okay, and we already know that base 10 is not really the best base to use, especially in computer science. So from time to time, you might want to say, I don't want to look at this from the base 10 perspective. Give me the base 16 representation. So in GDB, you can always type help. You can find out how to format print, like in this case. So let's keep going. And you can specify the formatting, which is FMT, which is the last portion of this help here. and it sees, and then it says, oh, by the way, this is a pointer. Go see the X command to find out how to use format. Now, I already know how to use the format, but I want to show you how to get help when you're trying to figure out how to use GDB. So you type help X, and now it explains how to specify the format. So the format says if you want things to be printed as in octal, which is base 8, specify a /o, lowercase o. If you want hexadecimal, then you specify /x. If you want it to be decimal, /d. But this is signed interpretation. If you want to interpret the bit pattern as unsigned, you do a /u. And you can even do a /t, okay, if you want a binary representation. So we can try all of this stuff here. So let's go ahead and print it as hexadecimal first. And we go like, oh, okay, I'm feeling much better now because it is at least printing out what I entered. Okay, that is great. Now we want to say, what about binary? Okay, if I look at x as a binary number, whoa, hold on a second here. Now you can count all the digits, and you'll find that there are only 63 digits over here, not 64. Because the leading 0 is cut out. The leading 0 is cut out because that's just a convention of doing things. We do not print leading zeros. But if you include an extra leading 0, then we have actually 64 bits over here. All right. So are there any questions about what I'm doing right now in GDB? So what if the leading bit is a 1, then it would print 64, actually 64 digits. It would just not print any leading zeros. All right, cool. So this is really kind of helpful, right? So we look this up and we go like, is there a way to look at things as a double? Nope, there's no way to look at it as a double. But wait, you guys remember typecasting from C and C++, right? So let's do this cast over here, okay? We want to look at X as a double. Now, I can tell you this is not going to work already because it's going to print this out, okay? In other words, it's about the same thing, except the casting is done to the value of X. In other words, the first thing the compiler or the debugger in this case is going to do is look at the value of X. We are not casting the value of X, excuse me, we're not changing the way we look at the bit pattern of X. We're only changing, we're casting this gigantic integer into a double, which is then printed like this. That's why it is not working, because we are not changing first the way we look at those 64 bits. We look at those 64 bits as an unsigned 64-bit number, get the value out of it. Then we cast the value into a double. And that is why this method does not work. Okay, that will not work either. Okay, print /t double x is not going to work either because once again, the cast is not applied to change. It's not changing the way we look at the bit pattern. X is evaluated first, and after X is evaluated, which gives us this particular value, then it is casted to a double. Then after it is casted to a double, then, oh, okay, I see. Yeah, it's still not working because what I want to do is to see 11. And this is certainly not 11. So we got back the bit pattern, but that's not what I want because, if I wanted to get back the bit pattern, this already did it. I want to see 11. I want the debugger. That won't do it either because it's already doing that by default. If I do a print /ux, it's already doing it with print x because x has a type of unsigned. So it's already doing it implicitly. Okay, so all of these methods are not working. So now I want to work on this step by step. So don't copy, don't write down anything. I mean, the whole thing is being recorded, so there's no need to write down anything. But you might want to put down a time mark of how to reinterpret the same bit pattern differently so that we can look at a bit pattern that used to be a 64-bit unsigned integer, but we can now look at it as a double. Okay, so you might want to put in a time mark, which is 10:17 right now. Okay, all right, so let's work on this. So we start with x, but I don't want to interpret the value of x, okay? Because as soon as I interpret the value of x, the compiler or GDB will say, I know what you're talking about. You're talking about 64-bit unsigned integer. No. Don't do that. So the first thing I want to do is to take the address of x. So $x is the address of x, okay? So if I ask you what is the type of the address of x, it's going to be the address of a 64-bit unsigned integer. That is not going to be very helpful. So then I can typecast the address itself. So now, okay, using this cast, so double asterisk is a typecast operator, but it's not typecasting the value of x. It's typecasting the address of x. So instead of looking at the address of x as the address of an unsigned 64-bit number, now I'm looking at the address of a double. Okay, so this is really kind of interesting. So now, if you want to look at this from a perspective in reality, it's basically the same thing as rezoning a particular parcel number. It's still the same place, okay? But I'm rezoning it. This is not residential anymore. This is now commercial, okay? Then I can say, well, if it is a commercial site, I want UPS to deliver something to this commercial site. Give me a price quote of that. So the final asterisk, which is this one here, is now interpreting and say, let's find out what is the value of this location. What location are we talking about? It is the location of a double, because we casted the address already at this point, that we are looking at the address of a double. So now I'm looking at the value of the at the location of a double. So now it will print out, it will change the way it interprets those particular bits. And if I press the enter key, woohoo, we got 11. So this is a really good, this is excellent timing, okay, which I normally do not do, okay. It's 10:20 and we are exactly done with a demonstration of, how a double representation works. So do we have any questions about the demonstration? Which is mostly what you're seeing on the screen right now. This is the verification of the manual process of figuring out the value given a particular bit pattern of a double precision floating point number. Are we doing okay or not? All right. So assuming we are doing okay, because I'm not seeing any questions, I'm going to stop live streaming and take a break for about 10 minutes, and then I'll come back and answer any questions about the lab. And before I do that, I probably want to share with you guys the key of today's lab. It is already released, but I need to give you the key to actually do it. Oh, way too much. Go back up. Alright, so the key is just double. I'm going to put it in Discord too. There we go. So this one does have quite a bit of math in it. There's no restriction of how you figure out the math. If you want to use a calculator, it's perfectly okay. You can use mathematical functions on a scientific calculator, such as log, exponent, and stuff like that. You can even use a spreadsheet to help you figure out the answer, because I personally really like spreadsheets because it's easy to copy and paste equations, change it, parameterize it, have one cell to refer to another cell. So that's my personal preference, but you can do it any way you want as long as you're not having someone to do it for you. So because the whole point is to get you guys to understand the concept of a double, and the material for this lab is going to be useful in our next discussion of doubles on Monday. So there you go. I am going to stop live stream at this point.